the presentations, you learn something new even in basic presentations, but the hallway track is just indispensable.
All right, let's figure out how fast is in your Constexpr. So we have a problem. We want to count the number of prime numbers below a certain number. This code runs at an odd complexity of n to the power of 1.5, and can be run at runtime and compile time. And what we're going to do is we're going to compare the sum of compile time and runtime each time. And that will give us some idea about the number of sleepy statements in the compiler. So let's run it at runtime. This would be the point I told you that I ran all my experiments only once, and my numbers are not accurate, but I've included multiple fractional digits, so let's pretend they are. By that number, it looks like it ran at runtime. This is a Constexpr function, and we're compiling with O3, so I would assume this would get evaluated at compile time, but it's not. Clang yields something similar. So let's run this at compile time. I've changed that Constexpr to a consteval, and that's gonna not let the compiler get away with running this at a runtime. We get this compilation error that tells us, hey, there's a limit, Constexpr ops limit, and we need to apparently bump that. Clang gives us something similar, but it doesn't give us any option. So we're gonna drop Clang here and ignore it for the rest of the talk. Bumping that number, apparently there's another number that we need to bump, and that is the Constexpr bool limit. And doing that, now we compile and run this code for around 17.353 seconds. And that is only 13.44 times slower than our Constexpr version. And not all that time was spent on sleepy statements. Some of it was spent on UB checking our code. So what if we ran the Constexpr version with the same flags? Now the Constexpr version runs at a similar time. So I guess we know that the compiler is using these flags to figure out if it should run something at compile time or runtime. So let's lower these kind of limits as much as possible. I couldn't go lower than 10,000 because apparently standard library is also doing some stuff at compile time. So 10,000 it is. And now we're only 46.27 times faster than the Consteval version. But what if we made our own Constexpr? Now at this point, I'm going to ask, we're going to look at the process. It's going to be a two-stage process. We're going to generate first a header that's going to contain the value of our runtime evaluated value of the Constexpr variable. And then on the second stage, we're going to include that header and use that Constexpr value to construct our Constexpr variable. And doing all that, it takes 22.56 times faster than the Consteval version. Now, I'm going to ask you to pretend you didn't see all these macros and this was a reflection talk. But yeah, what we're doing here, first we're generating the header, we're streaming our value into the header, and then we're kind of overriding main, and also default constructing our Constexpr variable, just to make the compiler happy. And on the second stage, we're including that header and then constructing our Constexpr variable from that value in the header. So I flipped through the slides so that you couldn't tell, but there are a few shortcomings. I'm not going to go through them because they're details. So let's look at what's next. Before reflection, all those things could be done, but after reflection, really, it's just reflection. So we're IMC, we're hiring, that's it. Yeah, that's the end of the talk. And come find us, we're happy to talk. Yeah, thank you.